In 2010, a Nobel laureate at the University of Oxford published a book that quietly upended one of the most basic assumptions of modern cosmology. The Big Bang, Roger Penrose argued, was not the beginning of time. It was simply the most recent of many. Our universe, he claimed, is just one in an endless sequence. A cosmic chord played over and over, with each note hearing the faint echo of the one before. He called it Conformal Cyclic Cosmology, CCC for short. And since 2010, Penrose has staked his scientific reputation on a startling claim that the cosmic microwave background, the leftover light from our Big Bang, contains physical evidence of universes that came before ours. In the next 12 minutes, we walk through the strangest cosmological proposal of the 21st century. What it claims, why it might be true, and the very serious reasons most cosmologists are not yet convinced. The standard Big Bang model, which we explored in a previous episode, describes the universe with stunning precision from a tiny fraction of a second after the beginning. But the actual moment of beginning, what cosmologists call the singularity, is a place where general relativity breaks down. Density goes to infinity. Curvature goes to infinity. Our equations stop producing meaningful answers. For most cosmologists, the answer to what came before has been one of two things. Either the question is meaningless, time itself began at the Big Bang, so there is no before, or there is a before, but it lies behind a wall of physics we do not yet have. Quantum gravity, string theory, loop quantum cosmology. Take your pick. Penrose offered a third possibility. What if our equations do not break down at the Big Bang, but transition? What if the singularity is not a wall, but a kind of joint, a smooth mathematical handoff from one cosmic aeon to the next? The core of Penrose's idea relies on a property of geometry called conformal invariance. In conformal geometry, you can stretch and squash space, but as long as you preserve the angles between lines, you preserve the underlying mathematical structure. Distances and sizes can become essentially meaningless, while shapes remain. Penrose noticed something extraordinary about the late-stage universe. After all the stars have burned out, after all the black holes have evaporated through Hawking radiation, after roughly 10–100 years, the universe will contain only massless particles, photons mostly, plus gravitons. And massless particles do not experience time the way matter does. They have no internal clock. Distance, for them, becomes a meaningless concept. In conformal terms, a heat-dead universe and a Big Bang are mathematically equivalent. Penrose argued that this is not a coincidence. It is the mechanism. The far future of our universe is quite literally the Big Bang of the next one. The cosmos cycles through what Penrose calls aeons, each ending in heat death, each becoming the singular start of the next. Here is where Penrose's claim becomes empirical. He argued that if CCC is true, certain extreme events from the previous aeon should leave imprints on our cosmic microwave background. Specifically, supermassive black holes from the previous universe, when they finally evaporated through Hawking radiation, would emit gravitational wave bursts. Those bursts, transmitted through the conformal handoff, should appear in our sky as concentric circular patterns of slightly different temperature. In 2010, Penrose and collaborator Vahe Gurzadyan published a paper claiming to have found exactly these patterns in the WMAP data. They reported finding low-variance circles in the CMB at greater frequency than chance would allow, concentric rings centered on certain points in the sky. The cosmology community responded quickly. Within months, 3 independent teams reanalyzed the WMAP data using the same methods. They could not reproduce the result. The circles appeared to be statistical artifacts of the noise, not signals from a previous aeon. Penrose pushed back, refining his methods and looking at Planck data when it became available. As of 2025, the dispute remains unresolved. Penrose continues to claim the patterns are real and meaningful. The mainstream consensus is that they are not. Beyond the empirical dispute, CCC faces theoretical challenges. The first is that the model requires all matter in the universe to eventually become massless. This works for protons if they decay, and proton decay is a real prediction of grand unified theories. But the predicted lifetime is at least 1034 years, and we have never observed it. Without proton decay, CCC's mathematical handoff doesn't work. The second problem is the cosmological constant. Our universe appears to be expanding at an accelerating rate, which means dark energy is real and the cosmos may never reach a true heat death. Instead, it may continue diluting forever in what some cosmologists call a big rip, or simply a slow asymptotic dilution. Penrose has proposed mechanisms to handle this, but they require additional assumptions that critics consider increasingly ad hoc. Third, and perhaps most important, CCC is not the only cyclic universe model. Paul Steinhardt and Neil Turok at Princeton and the Perimeter Institute have proposed an ekpyrotic cyclic model where universes collide and rebound through extra dimensions. Andre Lind at Stanford has proposed eternal inflation where universes bubble out of apparent inflating space-time indefinitely. Each of these models is internally consistent, mathematically serious, and produces somewhat different observational predictions. None has yet been confirmed. The deeper question Penrose's work raises is whether asking what came before the Big Bang is even meaningful. In our standard view, time and space were created together at the singularity. To talk about before is to use a temporal word in a context where time itself does not exist. It is, in St. Augustine's elegant 4th century formulation, asking what God was doing before he created the universe. When before is a notion that cannot precede creation. Penrose's answer is that before can be made mathematically meaningful, but only if we accept conformal invariance as a fundamental feature of the cosmos. Most physicists are not yet ready to make that leap. The deeper truth may be that our intuitions about time, born in a slow brain on a small planet during a brief intermission in cosmic history, are simply not equipped to ask this question well. Was there a before the Big Bang? We do not know. Penrose's model is one of the most beautiful, most rigorously argued attempts to give that question scientific meaning. Whether it is right, whether the rings he sees in the cosmic microwave background are real signals or statistical ghosts may be answered by data we have not yet collected. Gravitational wave detectors that can listen further back in cosmic time, or some clever observational test no one has thought of yet. Until then, we are left with the strangest possibility. That the silence at the beginning of our universe is not silence at all. That somewhere woven into the noise of the cosmic microwave background is the echo of a universe older than ours, ending its long, dim death just as ours was beginning to bloom. If you love careful, evidence-based exploration of the deepest questions in cosmology, subscribe to Cosmic Edge. We never sensationalize. We follow the equations to where they get quietly profound, and we are honest about where they end.